Welcome to Sleepy Stories. In this episode, we will take a clear and steady look at how the cosmos stays in motion. The purpose of this story is simple. It is here to help you learn something real and grounded about the universe while you rest. If sleep does not come right away, that is completely fine. You can still listen, still learn, and allow your body to relax at its own pace. Simply listen. Let your breathing slow, and allow the information to settle naturally. If you enjoy stories like this, you are warmly invited to like and subscribe. When people imagine the universe, they often picture vast stillness, dark space, silent stars, immense emptiness where nothing seems to move. This impression feels intuitive, especially when we look up at the night sky and see familiar patterns that barely change over a lifetime. Yet this sense of stillness is misleading. On every scale that science can observe, the universe is in constant motion. Movement is not an occasional event, it is the default condition. Nothing in the cosmos is truly at rest. What appears motionless is usually moving as part of a larger system. A star that seems fixed in the sky is traveling through its galaxy. That galaxy itself is drifting relative to others. Even the space between galaxies is not static. It is slowly expanding, increasing the distance between objects without requiring them to move through space in the usual sense. Stillness, when it appears, is almost always a matter of perspective. This idea becomes clearer when we consider how motion is measured. Movement only has meaning when compared to something else. An object can be stationary relative to one reference frame while moving rapidly relative to another. A person sitting quietly in a chair is not moving relative to the room, yet they are traveling with the rotation of the Earth's orbit around the Sun, and the Sun's path through the galaxy. All of these motions occur simultaneously, layered on top of one another. Because of this, absolute rest is not something physics easily defines. There is no universal background against which all motion can be measured. Instead, the universe is a network of relationships, with every object participating in multiple motions at once. This does not create chaos. On the contrary, it produces stability. Patterns emerge precisely because motion follows consistent rules. At the largest scales, motion shapes the structure of the universe itself. Galaxies rotate, clusters drift, and enormous filaments of matter slowly evolve over billions of years. These processes are not hurried. They unfold with patience, governed by gravity, energy, and time. The universe does not rush, yet it never stops. On smaller scales, the same principles apply. Planets move in steady paths because their forward motion balances gravitational pull. Atoms vibrate because energy cannot vanish. Heat flows, light travels, and particles interact continuously. Movement is not something added to matter, it is inseparable from it. This constancy of motion does not mean instability. In fact, long-lasting structures depend on it. A planet remains in orbit because it keeps moving. A star shines because energy flows outward from its core. Even the concept of time itself is tied to change. Without motion, there would be no way to mark one moment as different from the next. Understanding this can be quietly reassuring. The universe does not require perfect stillness to remain orderly. Balance does not come from freezing everything in place. It comes from continuous adjustment, from motion that follows reliable patterns over immense spans of time. As this story unfolds, we will explore how that motion began, how it is maintained, and why it never truly fades away. We will move gradually, step by step, through the forces and principles that keep the cosmos in motion, always at a calm and measured pace. For now, it is enough to recognize this single idea. The universe is not restless. It is active in a steady, predictable way. Motion is not a disturbance layered on top of reality. It is one of the foundations that allows everything else to exist. And as you continue listening, you can allow that thought to settle gently, knowing that constant movement and quiet stability are not opposites, but partners working together across the vastness of space. To understand why the universe never truly rests, it helps to look more closely at what motion actually means. In everyday life, movement feels simple. Something changes position, and we notice it. A car passes by. A clock hand advances. When nothing seems to change, we describe the situation as still. But in physics, stillness is far more elusive. Motion is always measured in relation to something else. There is no universal background that defines what it means to be truly motionless. Instead, every measurement depends on a chosen frame of reference. An object may appear stationary from one point of view while moving rapidly from another. Both descriptions can be correct at the same time. Consider a spacecraft drifting far from any planet. Inside, an object floating in the cabin may appear perfectly still. Relative to the spacecraft, it has no motion. Yet the spacecraft itself is traveling through space, carried by the gravity of stars and the expansion of the universe. Relative to distant galaxies, that same object is moving at extraordinary speed. The idea of rest dissolves once perspective changes. This relativity of motion is not a philosophical argument. It is a practical principle used in every branch of physics. There is no experiment that can reveal whether an observer is in absolute rest. All that can be measured are differences in motion between systems. Because of this, absolute stillness becomes a concept without physical definition. Even when systems appear calm, motion persists internally. Atoms vibrate as long as temperature remains above absolute zero. Electrons occupy dynamic states around atomic nuclei. On larger scales, air molecules drift, oceans circulate, and tectonic plates shift. These motions may be slow or subtle, but they never fully vanish. The same principle applies on cosmic scales. A star may seem fixed against the sky, but it moves through its galaxy, bound by gravity and inertia. The galaxy rotates, shaped by the mass within it. Groups of galaxies drift relative to one another as space itself expands. No layer of motion replaces another. They all coexist, stacked together across different scales. Because motion is relative, the universe does not need a central point or a preferred direction. There is no cosmic reference frame that defines true rest. Each observer carries their own perspective, shaped by their motion through space and time. This idea can feel unsettling at first, but it leads to a deeper understanding of stability. Stability does not require stillness. It requires consistency. When motions follow predictable rules, systems remain coherent. A planet maintains its orbit not by slowing down, but by continuing forward at the right speed. A galaxy retains its structure because the motions of its stars are balanced over time. The universe remains intelligible because motion obeys reliable laws. Time itself becomes meaningful through this lens. Without change, there would be no way to distinguish one moment from another. Clocks function because something moves in a regular way. A pendulum swings. An atom oscillates. A beam of light travels a fixed distance. Time is not something that exists independently of motion. It is revealed through it. This understanding reframes the idea of rest. Rest is not the absence of motion, but a condition where motion becomes steady and unchanging from a chosen perspective. It is local and temporary, not universal or absolute. In that sense, rest is a useful approximation, not a fundamental state. As you listen, there is no need to imagine the universe racing or rushing. Its motions are not frantic, they are measured and persistent. Relative motion allows everything to remain connected without collapsing into disorder. Nothing needs to stop for the universe to remain balanced. By letting go of the expectation of absolute stillness, the cosmos becomes easier to understand. Motion is not something that interrupts order. It is the quiet framework that makes order possible, moment after moment, across scales too large to fully grasp. To understand how motion became woven into the universe so deeply, it helps to look back to its earliest moments. Modern cosmology describes a beginning in which space and time themselves emerged together. This beginning is often called the Big Bang, but the name can be misleading. It was not an explosion into empty space. There was no surrounding void waiting to be filled. Instead, space itself began to expand everywhere at once. From that first moment, motion was already present, not as objects flying outward from a single point, but as distances increasing between all points. Every region of space moved away from every other region. not because they were pushed, but because the fabric connecting them was stretching. This distinction matters. It means the universe did not start with motion added later. Motion was present as soon as there was anything at all. In those earliest conditions, the universe was extremely hot and dense. Energy dominated everything. Particles formed, interacted, and transformed at rates far beyond anything that occurs today. These interactions were not random. They followed the same underlying principles that govern motion now, only under far more extreme conditions. Even then, energy shifted from one form to another, and nothing remained static. As the universe expanded, it cooled. This cooling allowed particles to combine into more stable forms. Protons and neutrons formed atomic nuclei. Later, electrons joined these nuclei to create atoms. Each step in this process depended on motion. Particles moved, collided, and redistributed energy. Without motion, structure could not emerge. Uniform stillness would have prevented complexity from forming at all. It is important to understand that this expansion did not slow to a halt after the universe became large. It continued. The distances between large-scale structures kept increasing, even as gravity locally gathered matter into stars and galaxies. These two processes are not in conflict. Expansion dominates on the largest scales, while gravity organizes motion on smaller ones. The universe grows while still forming structure within itself. Because expansion applies everywhere, there is no central origin point to locate. Every observer, wherever they are, sees distant galaxies moving away in all directions. This does not place the observer at the center. It reflects the fact that expansion is uniform. Motion is built into space itself, not imposed from outside. This early expansion also explains why the universe appears so smooth on large scales. Small differences in density were stretched across vast regions, creating gentle variations rather than abrupt changes. Over time, gravity amplified these small differences, pulling matter together in some regions while others became emptier. Motion, once again, did not erase structure, it enabled it. The idea that space can expand may feel abstract, but its consequences are observable. Light traveling through expanding space has its wavelength stretched along the way. This stretching shifts light toward longer wavelengths, an effect that can be measured. Through careful observation of this shift, astronomers reconstruct how the universe has expanded over time. Motion leaves traces that can be read long after the events themselves have passed. What began in those early moments never truly ended. Expansion did not switch off. Energy did not settle into a final configuration. Instead, the universe entered a long, gradual evolution, in which motion continued in quieter, more structured forms. The rapid interactions of the earliest era gave way to slower, more stable processes, but the underlying principle remained unchanged. From the beginning, the universe was not designed to reach a state of rest. Its initial conditions favored change, interaction, and transformation. Motion was not something the universe acquired, it was something it expressed as soon as it existed. As this story continues, that original expansion will remain in the background, shaping everything that follows. The stars, the galaxies, and even the largest structures we observe today still carry the imprint of that first, universal motion. It is not a distant historical detail, it is an ongoing process that continues to define the universe right now. The expansion that began in the earliest moments of the universe is not a relic of the past, it is still happening now. To understand how the cosmos stays in motion, it is essential to understand what expanding space really means, and just as importantly, what it does not mean. When we say that the universe is expanding, we are not describing galaxies racing outward through a pre-existing emptiness. Galaxies are not engines pushing themselves away from one another. Instead, the space between them is increasing. Distances grow because space itself grows. This distinction is subtle, but it changes how motion on the largest scales is understood. Imagine two distant galaxies that are not bound together by gravity. Over time, the distance between them increases even if neither galaxy is actively moving through space in the usual sense. From the perspective of each galaxy, the other appears to recede. This recession is not caused by propulsion or explosion. It is a geometric effect of expanding space. This expansion is remarkably uniform. On very large scales, every region of the universe behaves in the same way. There is no preferred direction and no special location where expansion originates. Each observer sees distant galaxies moving away in all directions, with more distant galaxies receding faster. This relationship between distance and recession is one of the clearest signatures of cosmic expansion. The evidence for this expansion comes from light. As light travels across vast distances, the stretching of space lengthens its wavelength. This shift moves light toward the red end of the spectrum. By measuring how much this red shift has occurred, astronomers can determine how much the universe has expanded during the light's journey. These measurements reveal a universe that has been growing larger for billions of years. What makes this especially important is that expansion does not overwhelm all other forms of motion. On smaller scales, gravity dominates. Stars remain bound within galaxies. Planets remain bound to stars. At these scales, the expansion of space is so weak that it has no measurable effect. Motion in the universe is layered. Expansion governs the largest structures, while gravity shapes motion locally. This layered structure allows stability to exist within change. Galaxies can rotate and evolve, even as the distances between galaxy groups increase. The universe does not tear itself apart. Instead, different forms of motion operate at different scales, each following the same underlying physical laws. Expansion also helps explain why the universe does not settle into equilibrium. As space grows, matter and energy become more spread out. Temperatures fall, interactions become less frequent across vast distances. Yet even as conditions change, motion does not cease. It simply shifts form, from rapid early interactions to slower, long-range evolution. Importantly, expansion does not require an external force acting on the universe from the outside. There is no surrounding space into which the universe expands. Expansion is an internal property of space itself. It is how the universe evolves according to its own rules. This ongoing growth gives the cosmos a quiet sense of direction, not a destination but a trend. Distances increase, structures drift apart unless gravity holds them together. The universe changes without urgency, without pause, and without any need to reach a final state of rest. As you continue listening, it may help to let go of the image of a static cosmic backdrop. The stage itself is moving, slowly and steadily. Space is not a fixed container. It is an active participant in the universe's motion, shaping how everything else moves within it. The expansion of the universe is not only continuing, it appears to be accelerating. This observation has led scientists to introduce a term that often sounds more mysterious than it needs to be. That term is dark energy. Despite its name, dark energy is not a clearly identified substance or force. It is a label for a measured effect. It describes what we observe, not necessarily what we fully understand. When astronomers study distant galaxies, they see that the expansion of space is not slowing down under gravity alone. Instead, over very large distances and long periods of time, the rate at which space expands seems to increase. This conclusion comes from careful measurements of light that has traveled across much of the observable universe. The data are consistent and repeatable. Something is influencing the large-scale motion of space itself. What dark energy represents, in practical terms, is the simplest explanation that fits those observations. It accounts for the acceleration without requiring immediate changes to well-tested physical laws. However, it does not yet tell us what the underlying cause truly is. Dark energy is a placeholder for a deeper mechanism that remains unknown. This uncertainty does not weaken the science. It reflects how scientific understanding progresses. Measurement comes first, explanation follows later, sometimes much later. The history of physics contains many examples where effects were observed long before their causes were fully understood. Gravity itself was described mathematically centuries before its deeper nature became a subject of modern theory. What matters for understanding cosmic motion is that dark energy, whatever its origin, influences space on the largest scales. It does not disrupt galaxies, stars, or planetary systems. Its effect is extremely weak locally. Only across vast distances does it shape the overall behavior of the universe. motion once again reveals itself as layered and scale-dependent. This perspective also helps prevent unnecessary tension between certainty and uncertainty. Scientists know that expansion is accelerating. They know how to measure it. They can predict its effects on large-scale structure. What they do not yet know is why space behaves this way. Both statements can be true at the same time. Rather than introducing instability, this unknown adds coherence to the story of cosmic motion. The universe does not drift aimlessly. Its behavior follows consistent patterns that can be observed and tested, even when some underlying causes remain incomplete. Motion continues not because everything is fully understood, but because the universe operates according to rules that hold whether or not they are fully explained. There is also something quietly calming in this approach. The cosmos does not require complete answers to function smoothly. It moves forward according to its nature, guided by principles that reveal themselves gradually through observation and time. As space continues to expand, and as its expansion subtly accelerates, the universe does not rush toward an abrupt outcome. It evolves slowly, with patience. Motion remains steady, persistent, and deeply woven into the structure of reality. With this understanding, we can move on from the largest scales back toward the forces that shape motion more locally. Gravity, rotation, and balance begin to dominate the story again. The universe stays in motion not because of a single cause, but because many influences work together, each within its own domain, all contributing to a cosmos that never truly stands still. While the expansion of space shapes motion on the largest scales, gravity becomes the dominant influence when matter is close enough to interact. Gravity does not oppose motion in the way it is often imagined. It does not bring everything to rest. Instead, it reshapes how objects move, guiding them into paths that can remain stable for immense periods of time. Gravity works by altering direction rather than eliminating speed. When an object falls toward another, it does not simply slow and stop. It accelerates, curving its path inward. If that object already has forward motion, gravity bends that motion into an orbit. This is why planets circle stars and stars circle the centers of galaxies. Motion continues, but it is organized. This organizing role is essential. Without gravity, matter would disperse more uniformly as space expands. Structures would struggle to form. Gravity counteracts that tendency locally, pulling matter together and allowing complex systems to emerge. It does not freeze those systems in place. It keeps them moving in predictable ways. On planetary scales, gravity maintains balance. A planet remains in orbit because its forward motion and gravitational attraction are matched. If the planet moved too slowly, it would fall inward. If it moved too quickly, it would drift away. The orbit persists because motion is continuously adjusted, not because it stops changing. Stability is dynamic, not static. The same principle applies on much larger scales. Stars orbit within galaxies. Galaxies orbit within clusters. Each level of structure involves countless objects moving simultaneously, each influenced by the combined gravitational pull of many others. The result is not chaos, but long-term coherence. Patterns endure because motion is shared and constrained by mutual influence. Gravity also shapes motion over time. As systems evolve, energy is redistributed. Some objects gain speed, others lose it. Orbits shift gradually. Yet even as configurations change, motion itself remains. Gravity does not erase movement. It redirects it. This redirection allows the universe to remain active without becoming unstable. Matter does not collapse into a single point, nor does it disperse completely. Instead, it forms long-lasting arrangements that persist for billions of years. These arrangements are not fixed, they breathe slowly, adjusting as energy flows through them. Understanding gravity in this way changes how rest is perceived. What looks like stillness is often a balance of opposing motions. A star appears steady because the movements within it are symmetrical. A galaxy appears calm because the countless stellar motions average out. Beneath the surface, everything remains in motion. Gravity, then, is not a force of quiet. It is a force of structure. It keeps motion meaningful, allowing the universe to build and maintain complexity over time. Without it, motion would lose its ability to create lasting form. As we move forward in this story, gravity will remain a central thread. It does not interrupt the universe's motion. It gives that motion shape, rhythm, and continuity, allowing the cosmos to stay in motion without ever falling apart. When gravity organizes motion on the scale of entire galaxies, one of the most striking results is rotation. Galaxies do not simply sit in space as scattered collections of stars. They turn. Vast systems containing billions of stars rotate together around a shared center, maintaining their structure across immense spans of time. This rotation did not appear suddenly. It emerged gradually, as matter in the early universe began to gather under gravity. Small differences in motion, present from the beginning, were preserved and amplified as clouds of gas and dark matter collapsed. As material fell inward, any slight sideways motion became more pronounced. This is a natural consequence of conserving angular momentum. As the system contracted, its rotation increased. Once established, this rotation did not fade away. There is no mechanism in empty space that easily removes angular momentum from a galaxy as a whole. Without strong friction or external forces, rotation persists. The galaxy continues to turn, not because it is being driven, but because nothing is stopping it. This persistent rotation plays a crucial role in shaping galactic structure. In many galaxies, it leads to flattened disks where stars follow roughly circular paths. Spiral patterns emerge, not as fixed arms made of the same stars, but as regions where motion briefly aligns, creating waves of higher density. Stars move in and out of these patterns while the overall rotation continues. What is especially notable is that stars far from the galactic center move faster than visible matter alone would suggest. Their speeds remain high even where gravitational pull from luminous material should weaken. This observation tells us that the mass influencing their motion is not fully accounted for by what we can see. The explanation is addressed later in the story, but the pattern itself is clear. Motion reveals the presence of structure, even when that structure is not directly observable. Rotation also contributes to long-term stability. By distributing motion across the entire system, it prevents matter from collapsing straight inward. The balance between gravity pulling inward and rotational motion pushing outward keeps galaxies extended rather than compact. Again, stability arises not from rest, but from sustained motion. From a distance, a rotating galaxy may appear serene and unchanging. Its overall shape remains recognizable over millions of years, yet this calm appearance masks constant activity. Every star is in motion. Every orbit is slightly different. The system holds together precisely because these motions are coordinated through gravity and momentum. Galactic rotation illustrates a broader principle of the cosmos. Large-scale order does not require stillness. It requires continuity. When motion follows consistent rules and is shared across a system, structure can endure without ever becoming static. As we continue, the focus will narrow further, moving from galaxies as whole systems to the individual motions of stars within them. These smaller motions add depth to the larger pattern, showing how countless individual paths combine to create the stable, rotating forms we observe across the universe. Within a rotating galaxy, individual stars do not follow perfectly uniform paths. Each star moves according to the combined gravitational influence of everything around it. Nearby stars, vast clouds of gas, and the overall mass of the galaxy all contribute. The result is a complex pattern of motion that remains orderly without being simple. Most stars travel along paths that keep them bound to the galaxy, but these paths are not rigid tracks. Orbits can be slightly elongated, tilted, or irregular. Over long periods of time, small gravitational interactions cause gradual changes. A star may drift inward or outward. Its path may slowly precess. Yet, even with these variations, the star remains part of the galactic system. What makes this especially remarkable is how stable these systems are over enormous spans of time. A star can orbit the center of its galaxy for billions of years without being ejected or falling inward. This persistence depends on the shared gravitational field of the galaxy as a whole. Individual motions differ, but together they create a smooth, average structure that holds. The speeds of stars within galaxies also reveal something important about cosmic motion. Stars farther from the center often move faster than expected, based solely on visible matter. This means that motion itself becomes a tool for discovery. By observing how stars move, astronomers infer the presence of additional mass influencing those motions. The universe reveals its structure through movement, even when that structure cannot be seen directly. These stellar motions also help distribute energy and material. As stars pass through regions of higher density, they interact with gas and dust. Over time, this mixing influences star formation, chemical enrichment, and the long-term evolution of the galaxy. Motion is not only a means of maintaining structure, it is a way of renewing it. Despite all this activity, galaxies appear calm from afar. The individual motions blend together, producing a steady overall form. This apparent calm is not the absence of motion, but the result of many motions balanced together. Change occurs slowly, almost imperceptibly, when viewed on human timescales. Understanding this helps refine the idea of rest even further. A galaxy that looks unchanging is not frozen, it is dynamically stable. Countless movements continue beneath the surface, guided by gravity and momentum. Stillness is an impression created by scale and distance, not a true physical state. As the story continues, this same principle will appear again and again. Whether at the level of stars, planets, or particles, motion persists. It adapts, reshapes, and sustains the universe without ever needing to come to a halt. When attention shifts from stars to planets, the same principles of motion and balance appear in a more familiar form. Planets do not remain near their stars because they are held in place. They remain because they are constantly moving. An orbit is not a resting position. It is a continuous path shaped by motion and gravity working together. A planet begins its journey with forward motion inherited from the rotating disk of gas and dust from which it formed. Gravity from the central star pulls the planet inward, while the planet's forward motion carries it sideways. The combination of these influences produces a curved path. The planet falls toward the star, but it never reaches it. Instead, it keeps missing, tracing a repeating route through space. This balance is precise, but it is not fragile. Planetary orbits can remain stable for extremely long periods. Small disturbances may alter the shape of an orbit slightly, but the overall motion persists. Energy is exchanged gradually, not lost all at once. Motion continues because there is no efficient way for it to simply disappear. These paths are often described as fixed tracks, but they are better understood as ongoing processes. A planet is never in the same place twice, even when its orbit repeats. Each cycle carries subtle differences caused by interactions with other planets, radiation, and the slow evolution of the star itself. The orbit endures because it adapts, not because it is rigid. This dynamic stability allows planetary systems to exist long enough for complex processes to unfold. Surfaces cool, atmospheres form, chemical interactions proceed over immense spans of time. None of this would be possible if motion ceased. Rest would erase the conditions needed for development. Even within an orbit, motion is layered. A planet rotates on its axis while circling its star. The star itself moves through its galaxy. The galaxy drifts relative to others. Each layer adds to the total motion without cancelling the others. The result is not confusion, but coherence across scales. From a distance, planetary motion can appear gentle and repetitive, yet it is sustained by the same fundamental principles that govern galaxies and cosmic expansion. Gravity shapes the path. Momentum carries it forward. Time allows small adjustments to accumulate without breaking the system apart. By understanding orbits this way, motion becomes less dramatic and more dependable. It is not something that must be constantly renewed. Once established, it continues naturally, following rules that remain consistent across the universe. As the story moves on, this idea of conserved motion will deepen further. The reason planets, stars, and galaxies keep moving is not because they are pushed again and again, but because motion itself is one of the most persistent features of reality. The persistence of motion throughout the universe is closely tied to a principle that appears simple but reaches everywhere: This principle is the conservation of momentum. It states that once an object is moving, it will continue to move unless something acts to change its motion. In the quiet emptiness of space, there is very little to provide that change. Momentum combines mass and velocity. An object with mass that is already moving carries momentum with it. To remove that motion entirely would require an opposing influence equal in strength and duration. In everyday life, friction and resistance constantly drain momentum away. Air slows moving objects. Surfaces absorb energy. Motion fades because environments on Earth are dense and interactive. Space is different. Between stars and planets there is almost nothing to interfere. Without constant resistance, momentum remains. A planet continues along its orbit. A star keeps moving through its galaxy. A galaxy drifts relative to others. Motion does not need to be sustained. It simply persists. This principle helps explain why the universe does not gradually wind down into stillness. There is no universal friction acting on all objects at once. Energy and momentum are redistributed through interactions, but they are not erased. When two objects interact, momentum is exchanged, paths change, speeds adjust, yet the total motion remains accounted for. On cosmic scales, this leads to remarkable endurance. Systems formed billions of years ago still move in recognizable ways today. Orbits survive, rotations continue. Even when systems change, they do so by transferring motion rather than losing it entirely. Collapse in one region often leads to acceleration in another. Momentum also connects motion across different scales. The spin of a planet reflects motion inherited from earlier stages of its formation. That earlier motion traces back to the rotation of a protoplanetary disk, which itself formed from collapsing interstellar material. Each layer carries momentum forward, linking present motion to past conditions. This continuity gives the universe a sense of memory. Motion preserves information about how systems formed and evolved. By studying how objects move now, scientists infer the forces and events that shaped them long ago. Movement becomes a record written into space itself. Understanding momentum clarifies why motion feels natural rather than forced. The universe does not require constant input to stay active. Once motion exists, it tends to remain unless altered. Change happens through interaction, not decay into rest. As the story continues, this principle will appear again in new contexts, whether in clouds of gas, waves of energy, or the slow evolution of cosmic structure. Momentum underlies the universe's ability to stay in motion without effort or urgency. For now, it is enough to recognize this quiet consistency. Motion persists not because it is constantly renewed, but because it is conserved. The universe keeps moving because nothing demands that it stop. Beyond stars and planets, much of the universe exists in the form of gas and dust. These vast clouds fill the spaces between stars and stretch across entire regions of galaxies. They may appear diffuse and inactive, but in reality they are among the most dynamic environments in the cosmos. Motion within these clouds never fully settles. Interstellar gas is constantly shifting. Gravity draws material inward while pressure pushes outward. Shock waves from nearby stellar events ripple through clouds, compressing some regions while thinning others. Turbulence stirs material on many scales at once, creating patterns that change slowly but continuously. Nothing within these clouds remains fixed for long. Dust grains, though tiny, play an important role in this motion. They interact with gas, radiation, and magnetic fields, drifting and aligning in response. Over time, these interactions redistribute matter, allowing regions of higher density to form. Motion, even when gentle, creates differences. Those differences matter. Star formation begins, not with stillness, but with imbalance. A region of gas becomes slightly denser than its surroundings. Gravity strengthens there, drawing in more material. As gas flows inward, it does not fall straight down. Any small sideways motion causes rotation to increase. The cloud flattens, spins, and fragments. Motion becomes structure. This process unfolds over millions of years. There is no sudden transformation. Gas drifts, compresses, cools, and adjusts. Energy flows outward as heat and radiation. Momentum is redistributed but not removed. Even as a star begins to form, motion remains central. Material continues to spiral inward while excess energy escapes. What is striking is how orderly this complexity becomes. Despite turbulence and variation, the same basic patterns appear again and again across different galaxies. Motion guided by gravity and conservation laws leads to familiar outcomes. Stars form, systems stabilize. The universe repeats itself without becoming repetitive. These clouds also demonstrate how motion links different phases of cosmic history. Material expelled by old stars mixes into new clouds. Elements created in one generation become part of the next. Motion carries matter forward through time, ensuring that the universe does not reset, but evolves. From a distance, a cloud of gas may seem unchanged for thousands of years. On human timescales, it appears calm. Yet within it, countless small movements are underway. These motions are slow, but they are decisive. Over long periods, they shape entire regions of space. In this way, gas and dust remind us that motion does not need to be fast to be powerful. Persistence matters more than speed. Given enough time, even subtle movement transforms the universe. As we move forward, this idea of transformation through continuous motion will remain central. Energy changes form, structures emerge. Nothing is rushed, and nothing is truly still. Energy is one of the quiet reasons the universe never comes to rest. It does not behave like fuel that burns away and disappears. Instead, energy changes form while remaining present. This principle, known as conservation of energy, applies everywhere, from the smallest particles to the largest cosmic structures. It explains why motion continues even as systems evolve and cool. In the early universe, energy was concentrated and intense. Particles moved rapidly, interacting constantly. As space expanded, that energy spread out, temperatures fell, interactions became less frequent. Yet energy did not vanish. It transformed. Motion slowed in some places and intensified in others. Light carried energy away from dense regions. Matter retained energy in its motion, its structure, and its internal states. Today, energy appears in many forms at once. Stars shine because energy flows outward from their cores. Planets retain warmth because energy moves through their interiors. Even cold regions of space contain energy stored in motion, radiation, and fields. Nothing is completely inert. Where there is matter or radiation, energy is present in some form. This constant transformation keeps motion alive. When a star radiates energy into space, that energy does not disappear. It travels outward as light, warming dust, triggering chemical reactions, and eventually spreading thinly across the universe. Motion shifts location and expression, but it remains part of the system. Energy also connects motion across time. The movement of planets reflects energy inherited from the cloud that formed them. That cloud contained energy shaped by earlier stars. Each stage passes energy forward, altered but conserved. The universe does not reset. It carries its past into the present through continuous transformation. As energy spreads, systems gradually change character. Dense regions become more diffuse. Fast interactions give way to slower ones. Yet even this long-term trend does not produce stillness. Motion becomes gentler, more subtle, but it does not end. The universe evolves toward quieter forms of activity rather than toward absolute rest. This idea can be quietly comforting. Nothing needs to be forced to keep moving. Motion persists naturally because energy cannot simply stop existing. It shifts, flows, and redistributes according to reliable rules. Change is not a disruption. It is the normal outcome of conservation. If you are listening while resting, it may help to notice the parallel on a smaller scale. Your breathing moves energy through your body. Your heartbeat redistributes it rhythmically. Even as you relax, motion continues in a steady, balanced way. Rest does not mean stopping. It means allowing movement to settle into a calm pattern. The universe behaves in much the same way. Energy flows more slowly in some regions, more actively in others. Over immense spans of time, these flows shape everything that exists. Motion remains, not as urgency, but as continuity. As the story continues, this steady transformation of energy will reappear in many forms. It underlies time, structure, and change itself, ensuring that the cosmos stays in motion without ever needing to hurry. Time, as it is experienced and measured, is inseparable from motion. Without change, there would be no way to distinguish one moment from another. Every method humans use to track time depends on something moving in a regular way. A planet rotates, a pendulum swings, an atom vibrates. Time becomes visible only through motion. On a cosmic scale, this connection becomes even clearer. The age of the universe is inferred by observing how galaxies move apart. The history of stars is reconstructed by tracing how their energy output changes over time. Even the earliest moments of the universe are understood through patterns left behind by motion, frozen into radiation that still travels through space today. Time reveals itself as a record of change, rather than an independent backdrop. This does not mean that time is created by motion in a simple sense. Rather, motion gives time meaning. Without processes unfolding, time would have no markers. A universe in which nothing changes would offer no way to define before and after. In that sense, time and motion form a partnership. One does not become relevant without the other. This partnership also explains why time feels different at different scales. On human scales, changes are frequent and obvious. On cosmic scales, change is slow and subtle. Stars evolve over millions or billions of years. Galaxies shift and merge over even longer periods. From a brief perspective, these systems appear static. From a longer one, their motion becomes undeniable. The laws of physics treat time and motion as deeply connected. Motion through space and progression through time are woven together into a single framework. This is not an abstract idea reserved for theory. It has practical consequences. Clocks in motion tick differently than clocks at rest relative to an observer. Time responds to movement and gravity, adjusting in ways that can be measured with precision. Yet, despite this complexity, the overall message remains gentle. Time does not rush the universe forward. It allows motion to unfold at its natural pace. Processes are given room to develop fully, without urgency or interruption. Change accumulates slowly, guided by consistent rules. This understanding can soften the way time is perceived personally. Rest does not require time to stop. It requires allowing change to slow into a comfortable rhythm. Just as the universe does not demand constant activity to remain dynamic, the mind does not need to be busy to remain alive. As motion continues throughout the cosmos, time continues with it, quietly marking transitions without judgment. Together, they form the steady flow that carries the universe forward, moment by moment, without ever needing to come to a halt. Many of the most important motions in the universe are so slow that they are easy to overlook. On human timescales, they appear almost frozen. Yet these gradual movements shape everything that exists. The cosmos often operates in what might be called slow motion, not because it lacks energy, but because its scales are immense. Consider the motion of stars within a galaxy. A single orbit around the galactic center can take hundreds of millions of years. From one human lifetime to the next, the change is imperceptible. The sky looks the same. Patterns remain familiar. But over long spans of time, those stars trace vast arcs, subtly reshaping the galaxy's structure. Motion continues, patient and uninterrupted. The same is true for the evolution of galaxies themselves. They drift, interact, and sometimes merge, but these processes unfold over billions of years. What seems like a static arrangement of distant lights is, in reality, a constantly adjusting network of motion. The universe is active even when it appears calm. This difference in scale can create the illusion of stillness. When change happens slowly enough, the mind interprets it as stability. But stability in the cosmos is not the absence of movement. It is movement that unfolds so gradually that it remains balanced over time. Nothing needs to hurry. Given enough time, even the smallest motions leave a lasting imprint. Slow motion also allows complexity to develop. Stars burn steadily for millions or billions of years, providing long periods of consistent energy. Planets settle into enduring orbits. Chemical processes proceed without interruption. These extended durations are not a side effect, they are a feature. Without them, structures would be too brief to support richness or continuity. Understanding this can change how the universe is imagined. It is not a place of sudden events strung together by emptiness. It is a system where motion is almost always present, but rarely abrupt. Even dramatic phenomena, when viewed from a wider perspective, often emerge from long periods of gradual change. There is something quietly reassuring in this pace. The universe does not demand constant attention. It unfolds whether or not it is observed. Its motion does not depend on urgency or acceleration. It depends on persistence. As this story continues, the contrast between fast and slow motion will remain important. Some processes happen in moments, others take ages. Together, they create a universe that is always changing, yet rarely in a way that feels rushed. Motion remains steady, allowing everything to develop fully, at its own natural speed. When galaxies encounter one another, the event is often described as a collision. The word suggests sudden impact and destruction, but the reality is far slower and more measured. Galactic encounters unfold over hundreds of millions or even billions of years. They are among the clearest examples of how motion in the universe reshapes structure without haste. As two galaxies draw closer, their mutual gravity begins to alter their paths. Stars within each galaxy respond gradually, their orbits stretching and bending. Long streams of stars and gas can be drawn outward, forming extended tidal structures that arc through space. These features are not signs of chaos. They are the visible imprint of gravity, guiding motion over immense distances and long spans of time. Despite the scale of these encounters, direct collisions between stars are exceedingly rare. The vast distances between individual stars mean that most pass by one another without contact. What changes instead is the overall distribution of motion. Orbits adjust, energy is exchanged, the galaxies begin to interpenetrate, slowly settling into a new configuration. As gas clouds interact, their motion can become more complex. Compression increases in some regions, triggering new waves of star formation. Motion here becomes creative rather than destructive. Energy that once supported ordered rotation is redistributed, allowing new structures to emerge. Over time, the two galaxies may merge into a single, larger system with a different shape and pattern of motion. Throughout this process, nothing truly stops. The encounter does not halt motion, it transforms it. Rotational energy becomes random motion. Random motion becomes heat. Heat radiates outward. Each stage follows from the last, guided by conservation laws that remain intact even as structures change. From a distance, these mergers can appear dramatic, but they are never abrupt. The universe allows them to unfold slowly, giving every component time to respond. Motion adapts rather than breaks. The resulting galaxy may look calmer and more uniform, but beneath that appearance lies a long history of shared movement. These encounters remind us that change in the universe is often cumulative. Major transformations arise from extended interaction rather than sudden events. Motion weaves systems together, then gradually rearranges them into new forms. As the story moves forward, this idea will recur. Whether matter is gathering, dispersing, or reorganizing, motion remains continuous. Even the most significant changes in the cosmos respect the same quiet rule. Nothing is frozen, nothing is rushed, everything stays in motion, reshaping itself over time. Black holes are often described as places where motion ends. They are imagined as cosmic traps where matter falls inward and disappears into silence. This image is understandable, but it does not reflect how black holes actually behave. In reality, black holes are regions where motion becomes more intense, more organized, and more extreme than almost anywhere else in the universe. A black hole forms when a very large amount of mass collapses into a very small volume. This collapse does not erase motion. It concentrates it. Any material involved already carries momentum, rotation, and energy. As gravity strengthens during collapse, those properties do not vanish. they are preserved and amplified. This is a direct consequence of the same conservation laws that govern planetary orbits and galactic rotation. Because of this, matter approaching a black hole rarely falls straight inward. Even the smallest sideways motion becomes significant as gravity tightens its grip. Gas and dust begin to spiral, forming a rotating structure known as an accretion disk. Within this disk, motion accelerates dramatically. Material orbits faster and faster as it moves closer to the center, converting gravitational energy into heat through friction and compression. This heating is not subtle. Accretion disks can become some of the brightest objects in the universe, outshining entire galaxies. Energy is released as radiation across a wide range of wavelengths. Long before matter crosses the boundary of the black hole, enormous amounts of motion and energy have already been redistributed outward. In this sense, black holes are not merely sinks, they are engines that transform motion into radiation on a vast scale. Even the region near the black hole's boundary is defined by motion rather than stillness. From an external perspective, matter does not appear to freeze in place. It continues to move, orbit, and radiate. The extreme gravity alters how time and motion are experienced, but it does not eliminate them. The laws of physics remain consistent, even when applied under these extreme conditions. Black holes also influence their surroundings far beyond their immediate vicinity. Stars can orbit a black hole in stable paths for millions of years. Entire clusters of stars may move in coordinated ways around a central black hole without disruption. In many galaxies, including our own, a supermassive black hole sits at the center, while the galaxy continues to rotate and evolve around it. The presence of the black hole does not halt galactic motion, it becomes part of it. In some cases, black holes are associated with powerful jets that extend far into space. These jets are streams of energetic particles launched outward at high speeds, guided by magnetic fields and rotation. They demonstrate, once again, that black holes are not simply absorbers. They are sites where motion is redirected, focused, and projected outward over enormous distances. What makes black holes especially important to this story is that they represent the extreme limit of gravitational organization. If motion were ever going to break down, if the universe were ever going to reach a point where movement truly stopped, these environments would seem the most likely candidates. Yet even here, motion persists. It becomes more constrained and more energetic, but it does not vanish. This reinforces a broader principle that runs throughout the cosmos. Motion is not something that exists only under gentle conditions. It is fundamental. Whether in the slow drift of galaxies or the rapid spiral of matter around a black hole, the same underlying rules apply. Gravity reshapes motion, energy changes form, momentum is conserved, nothing simply comes to rest. Black holes also highlight the layered nature of cosmic motion. Their influence is powerful but localized. On larger scales, the universe continues to expand. Galaxies continue to interact. Clusters drift apart. No single object, no matter how extreme, overrides the broader patterns of motion that define the cosmos as a whole. Understanding black holes in this way removes much of the mystery that surrounds them. They are not exceptions to the universe's behavior. They are confirmations of it. They show that even under the most intense conditions imaginable, motion remains central to how reality functions. As the story continues, attention will move away from these extreme regions toward a quieter but equally important idea. Even where space appears empty, even where matter is sparse and interactions are rare, motion does not disappear. It persists in subtle forms, ensuring that the universe, at every level, remains active, structured, and alive with change. When people imagine empty space, they often picture absolute stillness, a perfect vacuum, nothing moving, nothing happening. This image feels logical. If there is no matter, no stars, no planets, then surely there is nothing left to move. Yet this idea does not match how space actually behaves. Even the emptiest regions of the universe are never truly still. To begin with, space itself is not passive. As described earlier, space expands. This expansion does not require matter to be present. Even vast cosmic voids, Regions where galaxies are extremely sparse participate in the same large-scale expansion as the rest of the universe. Distances within these regions increase over time. Motion continues, even where there is almost nothing to observe. But expansion is only part of the story. Empty space is also filled with energy in subtle forms. Fields extend everywhere, even where matter is absent. These fields can fluctuate, carry energy, and interact. They are not objects in the everyday sense, but they are not static backgrounds either. Their presence means that space always contains the potential for change. Light also travels through regions that appear empty. Photons can cross billions of light years without encountering matter, yet their journey is itself a form of motion. As they travel, they are influenced by the expansion of space, gradually stretching and losing energy. Even in near-perfect vacuum, motion leaves measurable traces. On very small scales, space is even less quiet than it seems. Quantum physics shows that empty space is not completely empty. Temporary fluctuations occur continuously. These are not particles popping in and out of existence in a simple sense, but brief variations in energy that arise naturally from the rules governing fields. They are subtle and fleeting, yet they demonstrate that stillness is not a natural state, even at the most fundamental level. None of this means that empty space is chaotic or noisy. These motions are extremely gentle. They do not disrupt large structures or produce dramatic effects under ordinary conditions, but they are real. They show that the absence of matter does not imply the absence of activity. Gravity also reaches into empty regions. Even where matter is sparse, gravitational influence from distant galaxies still shapes motion. Paths of light bend slightly. Matter drifts slowly in response to distant mass. These effects are weak, but over vast distances and long periods, they matter. Motion accumulates patiently. Cosmic voids provide a useful example. These enormous regions contain very little matter compared to the cosmic average, yet they are not static cavities. They grow as surrounding regions become denser. Matter flows gently outward from them toward filaments and clusters. The void itself expands faster than denser regions, guided by the same laws that govern the universe as a whole. Even emptiness evolves. This perspective changes how stillness is understood. Stillness is not the natural state of space. It is an approximation created by limited sensitivity and limited time. When motion is slow, subtle, or distributed across vast scales, it becomes difficult to perceive. The human mind fills that gap with the idea of rest. But the universe does not require matter to stay active. Motion is embedded in the structure of reality itself. Space stretches, fields fluctuate, energy travels, influence propagates. These processes do not pause simply because matter thins out. This idea also reinforces an important theme. Motion does not need to be dramatic to be essential. The universe does not rely on constant explosions or collisions to remain dynamic. It relies on quiet persistence. Even the most uneventful regions participate in the same ongoing processes as the busiest ones. For someone listening while resting, this can feel unexpectedly calming. Activity does not imply disturbance. Motion does not imply urgency. The universe moves gently where it can and energetically where it must, always following the same underlying rules. Empty space, then, is not a void in the sense of absence. It is a region where motion becomes minimal, spread thin and subtle, but never eliminated. The cosmos allows gradients rather than absolutes. There are degrees of activity, not on and off states. As this story continues, this understanding will become increasingly important. The universe stays in motion not because it is filled everywhere with matter, but because motion does not depend on matter alone. It depends on space, energy, and the laws that connect them. Even where almost nothing exists, something is still happening. Change continues. Motion persists quietly, ensuring that no part of the cosmos ever truly stands still. Some of the most powerful changes in the universe begin with motions so small that they are almost impossible to detect at first. These motions do not announce themselves. They do not arrive with sudden force or dramatic effect. Instead, they accumulate quietly, shaped by time and gravity, until their consequences become unmistakable. The large-scale structure of the universe is built from these subtle beginnings. In the early universe, matter was distributed with extraordinary uniformity. Density differences from one region to another were tiny, yet they were not zero. In some places, matter was slightly more concentrated than in others. These differences were minute, far smaller than anything the human senses could detect. But gravity responds to even the smallest imbalance. Where there was a little more matter, gravity became just a little stronger. That slight increase in gravitational pull caused nearby matter to drift inward. The motion was extremely slow at first. Over thousands of years, the change was negligible. Over millions of years, it became noticeable. Over billions of years, it reshaped the universe. Small motions, patiently amplified, grew into the vast networks of galaxies and clusters that now span cosmic space. This process reveals something essential about motion. It does not need to be fast to be effective. Speed matters far less than persistence. A gentle pull, applied consistently over immense time, can move enormous amounts of matter. The universe favors endurance over urgency. As matter flowed toward denser regions, motion became increasingly organized. Streams of material formed. These streams intersected, merged, and redirected one another. Gravity guided these motions into filament-like structures, vast bridges of matter stretching across space. Between them, emptier regions emerged, not because matter vanished, but because it was drawn elsewhere. Motion carved structure through redistribution rather than destruction. Importantly, these developments did not require precise tuning. They followed naturally from the laws governing gravity and motion. Once slight differences existed, amplification became inevitable. The universe did not need to plan its structure. Motion, guided by consistent rules, did the work. This principle extends far beyond the early universe. It continues to operate today in many forms. In a cloud of gas, a small density fluctuation can eventually form a star. In a galaxy, a slight imbalance can trigger waves of star formation. In a cluster of galaxies, gradual drift alters long-term arrangement. In each case, the process begins quietly and unfolds over time. There is a tendency to associate significance with dramatic motion. Explosions, collisions, and rapid acceleration capture attention, yet the universe is shaped just as profoundly by slow accumulation. Motion that seems insignificant in the short term can dominate outcomes when given enough time. The cosmos is patient. It allows effects to grow gradually without rushing them toward completion. This also explains why the universe appears structured rather than chaotic. If motion were dominated by random, abrupt changes, large-scale order would be difficult to maintain. Instead, motion is filtered through gravity and conservation laws. Small deviations are not erased. They are refined, channeled, and expanded into recognizable patterns. There is a quiet elegance in this process. The universe does not resist small beginnings. It embraces them. It allows minor variations to persist long enough for their influence to matter. In doing so, it builds complexity from simplicity without violating its own rules. This idea has implications beyond astronomy. It suggests that change does not require forceful intervention to be meaningful. Consistency matters, direction matters, time matters. The universe demonstrates that gentle motion, when allowed to continue uninterrupted, can transform entire systems. Even now, countless small motions are underway across the cosmos. Gas drifts, stars migrate slightly within their galaxies, galaxies move within clusters. These motions may never produce dramatic events within a human lifetime, but they are not inconsequential. They are the mechanisms by which the universe continues to evolve. For someone listening in a quiet moment, this can feel reassuring. Not everything needs to happen quickly to matter. Progress does not require urgency. The universe achieves its greatest transformations through patience and continuity. As this story moves forward, waves of motion will take a more explicit role. Some changes travel not through matter itself, but through space and fields. Yet, even there, the same principle holds. Small disturbances, carried faithfully across vast distances, can reshape understanding and reveal deep truths about how the cosmos stays in motion. Not all motion in the universe involves matter traveling from one place to another. Some of the most important forms of motion take the shape of waves. These waves do not carry objects across space. They carry energy, influence, and information. Through them, the universe communicates with itself across vast distances. Light is the most familiar example. It moves as a wave through space, even when there is no material medium to support it. From the moment a photon is emitted by a star, it begins a long journey, sometimes lasting billions of years. During that journey, it carries energy outward, linking distant regions of the cosmos. Motion here is not about displacement of matter, but about the propagation of change. As light travels, it interacts with the universe in subtle ways. Its wavelength stretches as space expands. Its path bends slightly as it passes massive objects. These effects are small, but measurable. By studying them, scientists reconstruct the motion of galaxies, the growth of structure, and the history of cosmic expansion. Light becomes a record of motion written across space and time. Beyond light, there are other waves that reveal even deeper layers of motion. Gravitational waves are ripples in space itself, produced when massive objects accelerate. When two dense objects orbit one another or merge, they disturb the surrounding structure of space. That disturbance travels outward at the speed of light, carrying information about the event that created it. Space itself moves, oscillating gently as the wave passes. These waves are extraordinarily subtle by the time they reach distant observers. The motion they cause is far smaller than the width of an atom, yet they are real. They can be detected. Their existence confirms that space is not rigid. It can stretch, compress, and vibrate, responding dynamically to motion elsewhere in the universe. What makes waves especially important is that they allow motion to influence regions far removed from its source. A collision between massive objects in one part of the universe can leave detectable traces billions of light-years away. Motion becomes a messenger, linking events across unimaginable distances. Waves also demonstrate that motion does not require permanent change to leave an imprint. After a wave passes, space returns to its previous state, yet the information carried by the wave remains known. The universe is capable of transmitting motion without permanently altering the medium through which it travels. This ability adds resilience to cosmic structure. On smaller scales, similar principles apply. Vibrations travel through matter as sound. Oscillations propagate through fields. Energy moves outward while the underlying structure remains intact. These patterns repeat across scales, suggesting a deep consistency in how motion behaves. Importantly, waves show that motion can exist without accumulation. Unlike matter gathering under gravity, waves pass through without building up. They bring change temporarily, then move on. This complements the slower, accumulative motions described earlier. Together, these two modes of motion allow the universe to both evolve gradually and respond instantly. Waves also connect motion to measurement. Many of the universe's properties are known only because waves reach observers. Light from distant stars, radiation left over from early cosmic conditions, subtle distortions caused by gravitational waves. Without these traveling patterns, the universe would be far more difficult to understand. Motion becomes the means by which knowledge itself is possible. This reveals another aspect of cosmic balance. Motion does not overwhelm structure. It does not shake everything apart. Waves carry energy delicately, dispersing it rather than concentrating it. They allow interaction without destruction. The universe remains connected without becoming unstable. Over immense timescales, wave-based motion contributes to cooling and equilibration. Energy radiates outward. Systems gradually lose intensity without losing coherence. Motion transitions from concentrated to diffuse forms, but it never disappears entirely. As this story continues, it becomes clear that motion in the universe is not limited to objects following paths. It includes vibrations, oscillations, and ripples that move through space itself. These forms of motion are quieter than collisions and orbits, yet they are just as fundamental. The cosmos stays in motion not only because matter moves, but because space can carry change. Through waves, the universe remains responsive, connected, and dynamic, even across distances so vast that direct interaction would otherwise be impossible. Stability in the universe is often misunderstood as a lack of movement. When something remains recognizable for a long time, it is easy to assume that it must be still. In reality, stability in the cosmos almost always depends on continuous motion. What endures does so not because it stops changing, but because its changes remain balanced. This idea appears at every scale. A planet maintains its orbit not by pausing in space, but by constantly moving forward while gravity bends its path. A star remains intact not because its interior is quiet, but because opposing processes remain in equilibrium. Energy flows outward from its core while gravity pulls inward, creating a long-lasting balance that can persist for billions of years. Motion does not disrupt stability, it sustains it. Galaxies offer a broader example. Their overall shapes can remain recognizable for immense spans of time, yet every star within them is moving. Orbits overlap, paths shift gradually, gas circulates, energy redistributes. The galaxy appears stable because these motions are coordinated. No single motion dominates enough to tear the system apart. Stability emerges from shared movement rather than from rest. This dynamic form of balance is more resilient than stillness would be. A perfectly static system would be fragile. Any disturbance, however small, could break it apart. A dynamic system, by contrast, can absorb change. Motion allows energy to be redistributed, stress to be relieved, and structure to adapt. The universe favors this kind of stability because it lasts. On the largest scales, this principle remains true. Galaxy clusters are held together by the combined gravitational influence of their members, even as those members move relative to one another. The cluster does not collapse or disperse quickly because motion is spread across many paths and directions. Balance is maintained through complexity, not simplicity. Even expansion fits within this framework. The universe expands, yet structures remain bound where gravity dominates. These two behaviors coexist without contradiction. Expansion governs the largest distances. Gravity shapes motion locally. The result is a universe that grows while retaining internal coherence. Stability and change operate together rather than in opposition. This perspective challenges the intuitive idea that rest is the safest state. In the cosmos, rest is rare and often temporary. When motion ceases entirely, systems lose their ability to respond. Energy differences flatten out. Time loses its markers. Structure fades. Stability without motion is not stability at all. It is stagnation. Dynamic stability also explains why the universe does not require constant correction. There is no external hand adjusting every orbit or regulating every interaction. Once systems form, their internal motions maintain balance naturally. Feedback processes smooth extremes. Excess energy radiates away. Deficits draw energy inward. Motion regulates itself. This self-regulating behavior is visible in many contexts. In stars, pressure increases when temperature rises, slowing further compression. In galaxies, increased density can trigger star formation, which then releases energy and alters local motion. These processes do not halt motion, they guide it into sustainable patterns. Over long periods, dynamic stability allows systems to evolve without losing identity. A galaxy today is not identical to what it was billions of years ago, yet it remains the same galaxy in a meaningful sense. Its motion has changed, but not in a way that erases continuity. The universe preserves form through gradual adaptation rather than through freezing. Understanding stability this way also reframes how change is perceived. Change does not imply failure of balance. It is often the mechanism by which balance is maintained. Small adjustments prevent larger disruptions. Motion distributes influence rather than concentrating it. This principle extends beyond astronomy. It reflects a deeper pattern in nature. Systems that remain flexible, responsive, and active tend to endure. Systems that resist all change become brittle. The universe demonstrates this principle on the largest scale imaginable. In the context of cosmic motion, stability is not a destination, it is an ongoing process. At every moment, forces interact, energy flows, and paths adjust slightly. The universe does not seek an end state of perfect stillness. It seeks continuity. As this story continues, this understanding will remain central. Motion is not something the universe tolerates, it is something the universe uses. Through motion, structures persist, patterns emerge, and balance is maintained across unimaginable spans of time. The cosmos stays in motion not despite its stability, but because of it. The motion of the universe is not only shaped by the forces acting today, but also by the conditions that existed at the very beginning. Small differences present in the early universe did not fade away. They were carried forward, preserved through motion, and amplified over time. In this way, the cosmos remembers its origins, not through static records, but through how things continue to move. At the earliest stages, matter and energy were distributed almost uniformly. Almost, but not perfectly. Tiny variations in density and temperature were present from the start. These variations were extremely small, yet they mattered. Motion ensured that they were not erased. Instead, gravity acted on them, slowly turning slight imbalances into long-term trends. Once matter began to respond to gravity, motion followed predictable paths. Regions that were slightly denser drew material inward. That inward drift altered surrounding motion, redirecting flows and changing trajectories. Over immense timescales, these effects compounded. What began as minute differences grew into the large-scale structures now observed across the universe. Chance played a role in determining where these early variations appeared, but chance did not act alone. The laws of physics constrained how motion unfolded afterward. Not every outcome was possible. Motion followed channels shaped by gravity, energy conservation, and momentum. Randomness influenced initial conditions, but order emerged through consistent rules. This interplay between initial variation and lawful motion explains why the universe appears structured rather than arbitrary. Galaxies are not scattered randomly. They trace filaments and clusters. Voids are not empty by accident. They formed as matter flowed elsewhere. Motion acted as a sorting mechanism, guiding matter into patterns without requiring deliberate design. Importantly, this process did not require repeated intervention. Once the early conditions were set, motion carried their influence forward naturally. The universe did not need constant adjustment to produce complexity. It needed time, continuity, and persistence. Motion provided all three. The same principle appears on smaller scales. In a forming planetary system, tiny differences in velocity and position determine which bodies grow larger and which remain small. In a star-forming cloud, slight variations influence where collapse begins. In each case, early motion leaves a lasting imprint. Systems evolve along paths shaped by their beginnings. This persistence gives motion a directional quality without implying a predetermined goal. The universe does not move toward a specific outcome. It moves forward from its starting conditions, exploring the possibilities allowed by its laws. History matters because motion preserves it. This helps explain why the universe does not repeatedly return to the same state. Even though physical laws are consistent, initial conditions differ from one region to another. Motion carries those differences forward, ensuring diversity rather than repetition. Similar structures form, but no two systems are identical. There is also a sense of continuity here. Nothing appears from nothing. Every movement reflects earlier motion. Every structure carries traces of past dynamics. The present state of the universe is not an isolated moment. It is part of an unbroken sequence of change. Over time, some effects become less visible. Expansion stretches differences across larger volumes. Energy spreads out. Motion becomes more diffuse. Yet even then, the influence of early conditions remains encoded in large-scale patterns. The universe evolves, but it does not forget. This understanding adds depth to the idea of cosmic motion. Motion is not only about where things are going, it is also about where they came from. It links past, present, and future into a continuous process. Change accumulates rather than resets. Seen this way, the universe is neither chaotic nor rigid, it is responsive. Small influences matter because motion allows them to persist. Large structures emerge not from sudden decisions, but from long-term consistency. The cosmos stays in motion because motion carries information forward. It preserves differences, amplifies patterns, and allows complexity to grow naturally. Nothing needs to be rushed. Given enough time, even the smallest beginnings can shape the largest outcomes. As motion unfolds across the universe, it does more than simply move matter from place to place. Over long periods of time, motion gives rise to order. This may seem counterintuitive at first. Movement is often associated with disturbance or disorder. Yet in the cosmos, enduring patterns emerge precisely because motion follows consistent rules and unfolds patiently. Order in the universe does not appear fully formed. It develops gradually, as matter responds to forces that act continuously. Gravity draws material inward, while motion prevents it from collapsing all at once. The result is not uniformity, but structure. Stars gather into galaxies. Galaxies assemble into clusters. Clusters trace vast filaments that stretch across space. These arrangements are not imposed from outside. They arise naturally from motion constrained by physical law. One reason order emerges is that motion allows matter to explore many possible configurations. Over time, unstable arrangements dissolve, while stable ones persist. A cloud of gas may begin in a chaotic state, with particles moving in many directions. As gravity acts, some motions cancel out while others align. Energy is redistributed. The system settles into a configuration that can endure. Motion acts as a filter, not by stopping change, but by favoring arrangements that remain balanced. This process is slow, but it is effective. The universe does not search randomly. It evolves through continuous adjustment. Small changes accumulate. Patterns that can absorb those changes without breaking apart survive. Patterns that cannot gradually disappear. Order is not forced. It is selected through persistence. Motion also creates feedback. When matter becomes denser in one region, gravitational pull increases there, drawing in more material. This reinforces the initial pattern. At the same time, energy released through radiation or movement prevents unchecked collapse. These opposing effects work together. Motion allows energy to flow outward while matter gathers inward, producing systems that are neither static nor unstable. The emergence of order is especially visible in rotating systems. Rotation spreads motion across many components, allowing a system to maintain coherence. In a rotating galaxy, stars move along varied paths, yet the overall shape remains recognizable. In a rotating disk around a young star, material settles into planes and rings. Motion organizes rather than disrupts. Order also depends on scale. On small scales, motion may appear irregular. On larger scales, those irregularities average out. Random movements of individual particles give rise to smooth flows. Countless local interactions produce global patterns. What seems chaotic in detail becomes orderly when viewed as a whole. Motion bridges these scales, linking microscopic behavior to macroscopic structure. Time plays a crucial role here. Order does not appear instantly. It requires sustained motion over long periods. The universe allows processes to unfold without interruption. There is no rush toward a final configuration. Systems evolve at a pace set by their internal dynamics. Motion provides continuity, giving structure time to form and stabilize. Importantly, order in the universe is never absolute. Structures are not fixed forever. They persist for long periods, then change. Stars exhaust their fuel, galaxies merge, clusters evolve. Yet, even as individual structures transform, the overall pattern of organized motion remains. The universe does not return to disorder. It reshapes order into new forms. This ongoing reorganization shows that order and change are not opposites. they are partners. Motion allows order to exist without becoming rigid. It permits adaptation. When conditions shift, systems adjust rather than collapse. This flexibility is one reason cosmic structures endure across billions of years. The same principles apply across different domains. In planetary systems, stable orbits emerge from motion balanced by gravity. In stars, layered structures form as energy flows outward and gravity pulls inward. In galaxies, spiral patterns arise from collective motion rather than from fixed components. Each example reflects the same underlying idea. Order emerges because motion is guided, not random. Seen in this way, the universe does not strive for uniformity. It supports diversity within constraint. Motion explores possibilities, while physical laws limit outcomes. The result is a cosmos rich in structure, yet governed by simple principles. Complexity arises without violating consistency. This perspective also clarifies why the universe does not settle into a static arrangement. Perfect stillness would eliminate the processes that generate and maintain order. Without motion, there would be no way for systems to respond to imbalance or redistribute energy. Order would decay rather than persist. Motion keeps structure alive. Over immense spans of time, this dynamic order continues to evolve. Patterns shift, new structures appear, old ones fade, yet the overall behavior remains recognizable. The universe stays intelligible because motion unfolds within stable rules. Order, then, is not something the universe reaches and keeps. It is something the universe continually produces through motion. As long as movement persists, structure can form, adapt, and endure. In this way, motion is not merely a feature of the cosmos. It is the mechanism through which order itself becomes possible. The Earth exists within the same network of motion that shapes stars and galaxies. It is not set apart from cosmic dynamics, but embedded within them. Every moment on Earth is influenced by movements that extend far beyond the planet itself, layered together in a way that is easy to overlook because of familiarity. The most immediate motion is rotation. Earth turns steadily on its axis, producing the cycle of day and night. This rotation is not incidental. It carries momentum inherited from the early formation of the planet, when dust and gas gathered and collapsed within a rotating disk around the young sun. That original motion has never been lost. It has been redistributed and adjusted, but it continues, uninterrupted, shaping daily rhythms. At the same time, Earth moves along its orbit around the sun. This path is not a static track etched into space. It is a continuous balance between forward motion and gravitational pull. Earth is constantly falling toward the sun while also moving sideways fast enough to remain in orbit. This motion is stable because it is dynamic. Small variations occur, influenced by the gravitational presence of other planets, yet the overall pattern persists across immense spans of time. The sun itself is not stationary. It travels through the Milky Way galaxy, orbiting the galactic center along with billions of other stars. This journey takes hundreds of millions of years to complete. During this motion, Earth and the rest of the solar system are carried along, tracing a path through regions of the galaxy with different densities, radiation environments, and stellar neighborhoods. Planetary motion is therefore nested within stellar motion, which is itself nested within galactic motion. Beyond that, the Milky Way participates in larger patterns. It moves relative to nearby galaxies, bound together in a local group. This group drifts within a larger cosmic structure shaped by gravity and expansion. Each layer of motion adds to the total without cancelling the others. Earth's path through the universe is a composite of many overlapping movements, all proceeding simultaneously. Despite this complexity, life on Earth experiences a sense of stability. The ground feels solid. The sky follows predictable patterns. Seasons repeat. This stability does not arise from stillness. It arises from regularity. The motions affecting Earth are consistent enough to create reliable conditions. Rotation produces a steady cycle of light and darkness. Orbital motion produces predictable seasons. Larger cosmic motions change so slowly that their effects unfold gently over time. This layered motion also influences Earth in subtle ways. The tilt of the planet's axis, itself a product of early interactions and collisions, shapes climate patterns and seasonal variation. Gravitational interactions with the Moon influence tides, redistributing energy across oceans and affecting atmospheric circulation. These motions do not disrupt life. They support it by creating cycles and gradients that allow complex systems to function. Even beneath the surface, motion continues. Earth's interior remains active. Heat flows outward from the core. Tectonic plates drift slowly, reshaping continents over millions of years. Volcanic activity releases energy stored deep within the planet. These processes reflect the same principles seen elsewhere in the universe. Energy moves, matter responds, change unfolds gradually. Earth's position within the cosmos also affects how time is experienced. The planet's motion provides natural clocks. A rotation marks a day. An orbit marks a year. These cycles are not arbitrary. They arise from motion that has persisted since the solar system formed. Time, as measured on Earth, is inseparable from these enduring movements. It is also worth noting how Earth's motions are protected by their context. The planet's orbit remains stable because of the Sun's mass and the spacing of other planets. The solar system avoids frequent catastrophic interactions because of its location within the galaxy. These conditions are not static safeguards. They are outcomes of motion distributed in a way that favors long-term balance. This perspective emphasizes that Earth is not sheltered from cosmic motion, it is sustained by it. The same laws that govern galaxies and stars operate here, shaping the environment in which life developed. There is no sharp boundary between terrestrial and cosmic dynamics. One flows naturally into the other. Understanding Earth as part of this larger motion can change how stability is perceived. Stability does not require isolation. It requires integration into a system where motion is shared and regulated. Earth remains habitable not because it stands still, but because it moves in harmony with larger patterns. Over long periods, these motions will continue to evolve. Orbits will shift slightly, the Sun will change as it ages, the galaxy will rearrange itself through interaction. None of these changes happen abruptly on human timescales. They unfold slowly, guided by the same principles that have governed motion since the beginning. Earth's story, then, is not separate from the story of the universe. It is a chapter within it. The planet's motions echo the motions of the cosmos, scaled down and woven into local conditions. Life unfolds within this moving framework, supported by rhythms that are stable precisely because they are dynamic. In this way, Earth illustrates a central theme. Motion does not undermine continuity, it creates it. By participating in layered, predictable movements, Earth remains a place where change occurs without chaos, and where stability emerges not from rest, but from balance within motion. One of the reasons cosmic motion can be difficult to grasp is the difference between human time and cosmic time. Human experience is shaped by lifetimes measured in decades. Change is noticed when it happens within that narrow window. Anything slower than that often feels static, even when it is not. The universe, by contrast, operates on timescales that stretch far beyond direct experience. Many of the most important motions in the cosmos unfold over millions or billions of years. Stars evolve slowly, changing brightness and structure at a pace that would seem imperceptible without long-term observation. Galaxies shift their shapes and positions gradually, responding to gravity and interaction over spans of time far longer than recorded history. From a short-lived perspective, these systems appear unchanged. From a longer one, they are in constant transformation. This difference in timescale affects how motion is interpreted. A mountain range feels permanent, yet it is shaped by slow tectonic motion. A coastline appears fixed, yet it moves as continents drift. These examples on Earth offer a smaller scale parallel to cosmic processes. The change is real, but its pace places it outside everyday awareness. The universe magnifies this effect by many orders of magnitude. Cosmic time allows motion to act gently. There is rarely a need for sudden adjustment. When forces act over long periods, they shape matter without violence. Orbits shift smoothly, structures settle gradually, energy redistributes without abrupt release. This slow pace contributes to the universe's overall stability. Motion does not overwhelm systems because it unfolds patiently. The contrast between short and long timescales also explains why certain events feel exceptional. Supernova explosions, stellar collisions, or rapid accretion events stand out because they compress large amounts of change into relatively brief periods. Even these events, however, are often the culmination of long preparation. A star explodes only after millions of years of gradual evolution. Motion builds toward dramatic moments rather than producing them spontaneously. Understanding cosmic time also reshapes expectations about endings. On human scales, processes often have clear conclusions. A journey ends, a task is completed. In the universe, processes tend to transform rather than conclude. A star does not simply stop, it changes state. A galaxy does not reach a final arrangement. It continues to evolve through interaction and internal motion. Time enables continuity rather than closure. This long view reveals why motion remains persistent. There is no deadline toward which the universe is rushing. Without urgency, motion can be conserved, redirected, and repurposed rather than exhausted. Energy spreads, but it does so gradually. Systems cool, but they do not freeze all at once. Time gives motion room to adapt. Cosmic time also highlights the layered nature of change. Some processes operate quickly even on large scales. Others are extremely slow. These layers coexist. Fast motions play out within slower frameworks. Rapid interactions occur within structures that evolve gradually. The universe accommodates both without conflict because time allows them to unfold at their respective rates. This layering helps explain why the universe remains intelligible. Physical laws apply consistently across time. Motion follows predictable patterns, whether it unfolds over seconds or over billions of years. The difference lies not in the rules, but in the pace. Time stretches the same principles across vastly different scales. Human observation has adapted to this challenge through accumulation. Astronomers compare light from objects at different distances, effectively looking back in time. By assembling observations from many epochs, they reconstruct long-term motion that no single observer could witness directly. Motion becomes visible through patience and inference rather than direct experience. This approach reinforces an important idea. The universe does not need to be witnessed moment by moment to remain coherent. Motion continues whether it is observed or not. Time flows independently of attention. Structures evolve according to their own internal dynamics, guided by forces that do not depend on perception. Recognizing the role of cosmic time can also soften the impulse to impose human expectations on the universe. Change does not need to be immediate to be meaningful. Stability does not require permanence. The universe demonstrates a form of continuity that allows transformation without urgency. Over long periods, even the most stable arrangements will change. Orbits shift, stars age, galaxies rearrange. Yet these changes do not imply instability. They are the natural expression of motion unfolding within time. The universe remains active without becoming frantic, patient without becoming inert. This perspective helps reconcile motion and calm. Motion does not imply haste, time does not demand completion. Together, they allow the cosmos to evolve steadily, carrying its past forward while remaining open to new configurations. By appreciating the scale of cosmic time, it becomes easier to understand why motion never truly stops. There is always room for change to continue, always time for motion to express itself in new forms. The universe stays in motion because time itself allows movement to persist without exhaustion or finality. Motion is not only a feature of the universe, it is a requirement for complexity. Without movement, matter would remain evenly distributed. Energy differences would flatten out, and structure would fail to develop. The richness observed in the cosmos depends on the fact that motion creates gradients, interactions, and opportunities for change. At the most basic level, motion allows energy to flow. Heat moves from warmer regions to cooler ones. Radiation travels outward from stars. particles collide, exchange energy, and shift trajectories. These processes prevent the universe from settling into uniformity. Differences are preserved long enough for structure to form. Motion sustains imbalance, and imbalance makes complexity possible. Stars provide a clear example. A star shines because energy moves from its core toward its surface and then into surrounding space. This outward flow balances gravity pulling inward. If energy stopped moving, the balance would collapse. The star would either contract or disperse. Its layered structure depends entirely on continuous motion within and around it. The star exists as a stable object only because energy never stops flowing. Planetary systems depend on motion in a similar way. Orbits maintain spacing between bodies. Rotation distributes heat across surfaces. Atmospheric circulation transports energy from one region to another. Without these movements, conditions would become extreme and inhospitable. Motion moderates environments by preventing accumulation and stagnation. On a chemical level, motion enables reactions. Molecules must encounter one another to interact. Diffusion spreads substances through space. Thermal motion allows atoms to rearrange into new configurations. Even at very low temperatures, some motion remains, permitting slow processes to continue. Chemical complexity emerges because motion keeps systems from locking into rigid patterns. Biological systems, where they exist, depend even more directly on motion. Energy flows through metabolic pathways. Nutrients are transported. Waste is removed. Information moves through signaling processes. Life does not pause and resume. It continues through constant internal motion. While biology extends beyond the scope of cosmic physics, it rests on the same underlying principle. Motion enables organization rather than destroying it. The universe supports complexity not by suppressing motion, but by regulating it. Forces such as gravity, electromagnetism, and pressure guide movement into channels that allow structure to persist. Motion becomes patterned rather than random. This patterned motion allows systems to maintain identity while still adapting. Importantly, complexity does not require high speed. Many of the most intricate systems develop slowly. Planetary climates evolve over long periods. Chemical enrichment of galaxies unfolds across generations of stars. The universe allows complexity to arise gradually because motion is conserved and sustained rather than rapidly dissipated. Expansion also plays a role here. As the universe grows larger, matter becomes more spread out. Interactions become less frequent on the largest scales, yet local regions remain active. Expansion does not eliminate complexity. It isolates it into pockets where motion and interaction remain intense enough to sustain structure. Galaxies become islands of complexity within an expanding background. This separation between large-scale simplicity and local complexity is one of the universe's most effective strategies. Motion distributes matter unevenly, creating regions where processes can continue for long periods without interference. Complexity thrives where motion is neither too violent nor too weak. The universe naturally produces these balanced conditions. There is also a directional quality to complexity driven by motion. Systems tend to evolve from simpler arrangements toward more structured ones, not because they aim to do so, but because motion explores possibilities. Stable configurations persist, unstable ones dissolve. Over time, this selective process leads to an increase in organized structure within local regions, even as overall energy becomes more diffuse. This does not violate fundamental physical laws. While local complexity increases, the universe as a whole trends toward greater energy dispersal. Motion reconciles these tendencies by allowing structure to form temporarily without halting long-term redistribution. Complexity is sustained within the flow, not against it. This balance explains why the universe appears both orderly and dynamic. Structures form, evolve, and eventually transform, but new ones continue to arise. Motion prevents final outcomes. There is no permanent state of maximum complexity or complete simplicity. The universe remains open to change because motion never fully resolves into equilibrium. Understanding motion as a condition for complexity also clarifies why absolute stillness would be incompatible with any form of structure. Without movement, there would be no exchange, no adjustment, no response to imbalance. Systems would become locked and lifeless. Motion keeps pathways open. Even in regions where complexity is minimal, the potential for change remains. Energy moves, fields fluctuate, time continues. Motion preserves the possibility of interaction, even if conditions are currently sparse. The universe does not close doors. It leaves processes incomplete, allowing new arrangements to emerge when circumstances permit. This perspective reveals motion as a creative force, not in a deliberate sense, but in a generative one. By sustaining difference and allowing interaction, motion enables the universe to explore its own possibilities. Structure arises not because it is commanded, but because motion makes it unavoidable. Across the cosmos, from the smallest scales to the largest, complexity depends on the same quiet principle. Things move, energy flows, time allows accumulation. Without any of these, the universe would simplify itself into uniformity. Instead, it remains rich, varied, and capable of producing intricate arrangements. The universe stays in motion because motion keeps it interesting. Not dramatic, not chaotic, but capable of sustaining patterns that endure long enough to matter. It is possible to imagine, at least in theory, a universe in which motion completely stops. This idea appears occasionally in thought experiments, often framed as a final state where all change has ended. Yet, when examined closely, such a scenario reveals how deeply motion is embedded in the very definition of reality. Removing motion does not simply quiet the universe, it dissolves the conditions that make a universe describable at all. If motion were to cease everywhere, energy would no longer flow. Temperature differences would disappear as heat redistribution came to an end. Without gradients, there would be no direction for processes to follow. Matter would no longer interact in meaningful ways. Even the distinction between one location and another would lose clarity, because spatial relationships are defined through change and comparison. Time itself would become problematic. Time is measured through recurring motion or transformation. A second is defined by a specific atomic transition. A day is defined by rotation, a year by orbital motion. If nothing changed, there would be no physical process to mark the passage of time. The concept of before and after would lose operational meaning. A universe without motion would not merely be still, it would be timeless in any measurable sense. This reveals a deeper issue. Motion is not something that happens within time, it is one of the ways time becomes observable. Without motion, time would exist only as an abstract parameter with no physical expression. In practical terms, it would be indistinguishable from non-existence. A frozen universe would be one in which time could not be experienced or measured. Matter would also lose its defining behaviors. Atoms depend on internal motion. Electrons occupy dynamic states. Nuclei are not static assemblies. Even in their lowest energy configurations, particles retain quantum motion. Removing all motion would require removing these fundamental properties. Matter would no longer behave as matter. The structures that define physical objects would collapse into undefined states. On larger scales, gravity would lose its relevance. Gravitational interaction depends on the response of mass to curvature and force. Without motion, there would be no response. Objects would not fall, orbit, or interact. Gravity would exist only as an unexpressed potential. A force without motion would have no observable consequence. Even the idea of space would change. Space is not a rigid container. It is defined by relationships and distances that gain meaning through change. Expansion, curvature, and geometry are revealed through how objects and light move. In a universe without motion, space would lack observable structure. It would be mathematically describable, perhaps, but physically inert. From a thermodynamic perspective, complete stillness corresponds to a state where no energy gradients remain. This is sometimes described as a maximum entropy condition. Yet even this concept depends on motion to be meaningful. Entropy is defined through the number of accessible microstates, which themselves involve motion and variation. A truly motionless universe would not simply be at equilibrium. It would be beyond the conditions under which equilibrium can be defined. This highlights an important distinction. Equilibrium does not mean immobility. Systems in equilibrium often involve constant microscopic motion balanced in such a way that no net change occurs. A gas at uniform temperature still contains molecules moving at high speed. Motion persists, even when large-scale change stops. Complete stillness would require eliminating these microscopic movements, which contradicts known physical laws. Because of this, a universe without motion is not a realistic outcome predicted by any current theory. It is not where the cosmos appears to be heading. Even as energy spreads and structures thin out over immense timescales, motion remains. It becomes slower, more diffuse, and less concentrated, but it does not vanish. Processes continue, even if they become exceedingly gentle. This realization reframes how endings are imagined. The universe does not approach a final state of silence and immobility. It approaches conditions where change becomes subtle and spread out. Activity does not cease. It becomes quieter. Motion shifts from dramatic interactions to low-level, persistent processes that continue indefinitely. The idea of absolute stillness, then, serves a useful purpose as a contrast. It clarifies what motion provides. Motion enables time, structure, interaction, and meaning. Without it, the universe would not simply be calm. It would be undefined. The very concepts used to describe reality would lose their foundation. This understanding also removes the need to fear an eventual halt. There is no indication that the universe is running down toward a state where everything stops. Change may slow, but it does not end. Motion remains embedded in the laws governing energy, matter, and space itself. Seen in this way, motion is not a temporary feature awaiting exhaustion. It is a permanent condition. It can transform, spread, and diminish in intensity, but it does not disappear. The universe does not move towards stillness. It moves toward different expressions of motion. The absence of motion would represent not a final stage, but the absence of a universe that can be described, measured, or experienced. That such a state is unreachable is not a limitation. It is a reassurance. The cosmos remains capable of change precisely because motion cannot be fully removed. The universe stays in motion not because it resists rest, but because motion is inseparable from existence itself. When scientists consider the long-term future of the universe, they do not look for a moment when motion ends. Instead, they examine how motion changes character as conditions evolve. Current models suggest that the universe will continue to expand for an extremely long time. As expansion proceeds, distances between large structures increase, interactions become rarer, and the universe grows colder and more diffuse. Yet even in this distant future, motion remains present. As space expands, galaxies that are not gravitationally bound to one another drift farther apart. Over enough time, many regions of the universe will become isolated, with local groups of galaxies remaining connected internally while losing contact with more distant structures. This separation is not caused by galaxies accelerating through space, but by the steady growth of the space between them. Motion here becomes subtle, expressed as increasing separation rather than visible travel. Within these isolated regions, internal motion continues. Stars keep orbiting within galaxies. Planetary systems remain bound to their stars. Gas clouds drift and interact, though more slowly as available energy declines. Expansion does not erase these local dynamics. It simply reduces the frequency of large-scale encounters. Motion becomes more localized, but it does not vanish. Over very long timescales, stars will exhaust their fuel. Bright, active stars will give way to dimmer remnants. Galaxies will grow darker as star formation slows. These changes reflect the redistribution of energy rather than its disappearance. Energy spreads out, becomes harder to concentrate, and supports fewer intense processes. Motion shifts from energetic transformations to gentler forms. Even then, gravity continues to operate. Orbits persist. Objects respond to one another's presence. The universe does not freeze into a static arrangement. It evolves into a quieter state where change happens slowly and over great distances. Motion becomes less dramatic, but it remains fundamental. Importantly, none of these future scenarios involve motion stopping completely. They involve transitions from one regime of motion to another. The universe moves from being dense and interactive to being sparse and extended. Processes that once happened quickly now take immense time. This is not an ending in the traditional sense. It is a continuation under different conditions. There is also uncertainty in these projections. Future behavior depends on properties of space and energy that are not yet fully understood. Dark energy, whatever its underlying nature, plays a central role in shaping long-term expansion. If its influence changes over time, the future evolution of motion could follow different paths. Some possibilities involve accelerated expansion, others involve slower change. None predict absolute stillness. What is notable is how motion adapts rather than collapses. As environments change, motion finds new expressions. When dense matter becomes rare, radiation and fields dominate. When interactions become infrequent, persistence replaces activity. The universe does not lose its ability to move, it changes how movement manifests. This adaptability reflects a deeper consistency. The same conservation laws that governed the early universe remain in effect. Energy does not disappear. Momentum is not erased. Motion may spread out, but it remains accounted for. The universe does not discard its past. It carries it forward in altered form. From this perspective, the future of cosmic motion is not a story of exhaustion. It is a story of transformation. Activity becomes quieter, more diffuse, and less visible, but it does not cease. The universe continues to change, even if those changes unfold on timescales far beyond direct observation. This understanding also challenges the idea of a final state. A final state implies completion, an endpoint after which nothing happens. The universe, as currently understood, does not move toward such a condition. It moves toward ongoing evolution with diminishing intensity, not toward a halt. Motion in the far future may lack the complexity seen today. There may be fewer stars, fewer interactions, fewer concentrated sources of energy. Yet motion will still exist in the form of expansion, residual orbits, radiation traveling through space, and subtle field dynamics. Change continues, even if it becomes increasingly gentle. This gentle persistence is consistent with everything seen so far. From the earliest moments to the present, motion has shifted form without disappearing. There is no reason to expect that trend to reverse. The universe does not appear to be running down to nothing. It appears to be spreading out, carrying its motion with it. In this sense, the future of the cosmos mirrors its past. Conditions change, structures transform, the expression of motion evolves, but motion itself remains a constant presence, woven into the fabric of space, time, and energy. The universe stays in motion not because it must reach a destination, but because motion has no natural endpoint. It continues as long as the universe exists, reshaping itself quietly, patiently, and without final resolution. There are limits to how completely cosmic motion can be understood, not because the universe is deliberately obscure, but because knowledge itself is shaped by the tools available to gather it. Motion reveals much, yet it also sets boundaries on what can be known. Some aspects of the universe may remain partially hidden, not due to a lack of effort, but because of fundamental constraints built into observation and measurement. Much of what is known about cosmic motion comes from interpreting signals that travel across vast distances. Light carries information, but it does so at a finite speed. This means that observation is always delayed. Distant galaxies are seen as they were long ago, not as they are now. Motion is reconstructed from fragments of the past, assembled into models that describe how systems likely evolved. These reconstructions are powerful, but never complete. There are also regions of the universe that cannot be observed directly. Expansion creates horizons beyond which signals can never reach us. Motion continues in those regions, governed by the same laws, yet their details remain inaccessible. The universe contains activity that exists independently of being observed. Motion does not require awareness to persist. On smaller scales, Limits arise from the nature of matter and energy themselves. Quantum processes introduce uncertainty that cannot be eliminated, only constrained. Particles do not follow exact paths in the classical sense. Motion becomes probabilistic rather than deterministic. This does not imply randomness without structure. It reflects a different kind of order, one that operates through likelihood rather than certainty. These limits do not prevent understanding. They shape it. Science progresses by refining what can be measured and modeled, acknowledging uncertainty where it remains. Motion provides consistent patterns that can be tested, even when underlying causes are only partially known. The universe allows reliable prediction without requiring complete explanation. This balance between knowledge and uncertainty is not a flaw. It is a feature of a system that remains open to refinement. Motion ensures that the universe is never fully resolved into a finished description. New observations reveal new layers. Improved tools uncover subtler effects. Understanding deepens without ever reaching finality. There is also a practical limit imposed by scale. Some motions unfold so slowly that no civilization, no matter how long-lived, could witness their full progression directly. Other motions occur at energies so high or distances so vast that direct experimentation is impossible. In these cases, understanding relies on inference and consistency rather than direct manipulation. What remains constant is that motion continues whether or not it is fully understood. The universe does not pause until comprehension catches up. It evolves according to its laws, indifferent to the completeness of explanation. This independence reinforces the idea that motion is fundamental rather than contingent. Recognizing these limits can clarify expectations. The goal of understanding cosmic motion is not to eliminate mystery, but to describe behavior accurately within known constraints. Where certainty ends, consistency remains. Motion behaves in ways that are stable, repeatable, and coherent, even when their deeper origins are not fully resolved. This perspective allows space for curiosity without frustration. Unanswered questions do not undermine what is known. They mark the edges of current understanding. Motion does not become less real because it is not fully explained. It becomes more intriguing, inviting continued observation and refinement. The universe does not promise complete transparency. It offers patterns that can be followed, relationships that can be tested, and behaviors that remain reliable across time and scale. Motion sits at the center of this reliability. It provides continuity even as explanations evolve. In this sense, the limits of understanding do not constrain the universe. They define the ongoing relationship between observation and reality. Motion ensures that this relationship remains active. There is always more unfolding, more to observe, more to describe. The cosmos stays in motion regardless of what is known about it. Understanding grows alongside it, step by step, never fully complete, yet never disconnected from the reality it seeks to describe. There is a natural tendency to imagine that motion must eventually lead somewhere final. A state of rest, a completed arrangement, a moment when everything that can happen has already happened. Yet, when the universe is examined through what is known about its behavior, this expectation does not find much support. Motion does not appear to be something that runs toward a stopping point. It appears to be something that changes form without resolving into an endpoint. One reason for this is that motion in the universe is not a single process that can simply wind down. It is a collection of interconnected behaviors operating across many scales. Expansion acts on the largest distances. Gravity shapes local systems. Energy flows from concentrated regions to diffuse ones. Radiation travels through space. Fields fluctuate. These processes do not converge toward a shared finish line. They continue in parallel, influencing one another without cancelling each other out. Even when specific motions end, others take their place. A star stops shining when its fuel is exhausted, but the motion does not disappear. It transforms. Matter collapses or disperses. Energy is released. Radiation travels outward. Remnants continue to orbit, interact, and respond to gravity. What ends is a particular pattern, not motion itself. The same applies to larger structures. Galaxies merge and lose their distinct identities, but the resulting system still moves. Rotation changes, orbits redistribute, energy spreads. Nothing freezes into immobility. Change does not terminate motion. It redirects it. The idea of a final resting state often comes from everyday experience. On Earth, motion frequently ends because friction removes energy from systems. A rolling object slows, a swinging pendulum comes to rest. These outcomes feel intuitive because the environment is dense and resistive. Energy is quickly transferred into heat and dispersed locally. Space does not behave this way. There is no universal medium that drains motion efficiently everywhere at once. Even when energy becomes spread out, motion remains present in diffuse forms. Radiation continues to move, fields continue to fluctuate, expansion continues to separate distant regions. These motions may become less noticeable, but they do not vanish. The universe does not provide a mechanism that forces all motion to collapse into stillness. There is also no indication of a preferred final configuration toward which everything must evolve. Physical laws describe how systems change, not where they must end. They constrain behavior without prescribing outcomes. Motion follows rules, but those rules do not include an instruction to stop. This absence of a final resting point gives the universe an open-ended quality. It does not imply endless novelty or increasing complexity forever. Conditions can become quieter, interactions can become rarer, structures can thin out, yet the framework in which change occurs remains intact. Motion continues as long as space, time, and energy exist in any form. This perspective also explains why cosmic history does not resemble a journey with a destination. It resembles a sequence of transformations. Each stage arises from the previous one, carries some of its features forward, and modifies others. There is continuity without closure. Motion does not resolve itself. It evolves. Even equilibrium, when discussed in cosmology, does not mean stillness. It refers to a balance where large-scale change slows, not where all motion ceases. Microscopic motion persists. Expansion persists. Radiation continues to travel. Equilibrium describes a condition of reduced contrast, not of immobility. The absence of a final resting point also reinforces the idea that the universe is not designed around completion. There is no requirement that processes finish. The laws governing motion do not contain a concept of fulfillment. They describe relationships, not goals. Motion continues because nothing in the structure of reality requires it to end. This has implications for how time is understood. Time does not move toward a moment when it stops being relevant. It continues as long as change can occur. Since motion and change are inseparable, time remains meaningful without approaching a final chapter. The universe does not count down. It unfolds. There is something quietly consistent in this behavior. Motion does not need justification. It does not seek resolution. It persists because it is permitted by the laws that define existence. As long as those laws hold, motion remains possible. This understanding removes the expectation that the universe must eventually arrive at silence. Silence, in the absolute sense, is not a natural outcome of known physical processes. What is natural is transition. Motion shifts from one expression to another, from concentrated to diffuse, from rapid to slow, without terminating. Seen this way, the absence of a final resting point is not unsettling, it is stabilizing. It means the universe does not face an abrupt end to activity. Change becomes quieter, but it does not stop. Motion continues in ways that may be subtle but remain real. The universe stays in motion not because it avoids rest, but because rest, in the absolute sense, is not something the universe is structured to achieve. Movement is woven too deeply into the behavior of space, energy, and matter to be removed entirely. What remains is continuity. Patterns emerge, transform, and fade. New configurations arise from old ones. Motion links them together without demanding a conclusion. The cosmos does not pause to complete itself. It continues, not toward a destination, but as an ongoing process. In this way, motion defines the universe not as a story with an ending, but as a system that remains open to change for as long as it exists. Motion does not need to feel restless in order to exist. The universe demonstrates this quietly. Change unfolds without urgency. Movement continues without agitation. Across immense scales, motion settles into patterns that are steady, predictable, and calm. The cosmos remains active, yet it does not rush. It does not strain toward completion. It simply continues. This understanding allows motion and rest to coexist without conflict. Rest is not the absence of movement. It is a condition in which movement becomes balanced and unobtrusive. A planet at rest is one whose motion is so regular that it feels stable. A star at rest is one whose internal flows are balanced enough to endure. Even a galaxy that appears tranquil is sustained by countless coordinated motions beneath the surface. The universe offers many examples of this kind of calm continuity. Expansion proceeds gently, measured over billions of years. Orbits repeat with small variations that never accumulate into disruption. Energy flows outward in ways that gradually soften rather than shock. Motion remains present, but it does not dominate awareness. It becomes background rather than disturbance. This perspective reframes the idea of stillness. Stillness does not require everything to stop. It requires that nothing change abruptly. When motion follows reliable paths and unfolds at a pace that allows systems to adjust, it creates a sense of quiet. The universe achieves this naturally. Its motions are rarely sudden, most are gradual, layered, and spread across time. There is also reassurance in the fact that motion does not need to be maintained through effort. The universe does not expend energy trying to keep moving. Movement persists because it is conserved. Momentum carries forward. Energy changes form rather than disappearing. Space continues to expand without strain. Motion belongs to the structure of reality itself. This allows the cosmos to remain open rather than resolved. There is no final configuration waiting to be reached, no state of perfect rest to arrive at. Conditions change, expressions of motion evolve. Activity becomes quieter in some regions and more concentrated in others, yet nothing demands an ending. The universe remains in process rather than approaching closure. Within this ongoing movement, stability emerges naturally. Patterns repeat. Structures endure long enough to become familiar. Cycles establish themselves. These cycles do not trap the universe, they give it rhythm. Motion becomes something that can be relied upon rather than something that disrupts. This rhythm extends from the largest scales to the smallest. Galaxies rotate, planets orbit, atoms vibrate. Even in regions where matter is sparse, energy and fields continue to shift subtly. The universe does not contain zones of absolute inactivity. It contains gradients of motion, from energetic to gentle, from obvious to nearly imperceptible. The gentle end of this gradient is where calm resides, not because movement has stopped, but because it has become evenly distributed. Differences soften, contrasts fade. Change continues without drawing attention to itself. The universe demonstrates that this kind of calm does not require withdrawal from motion. It requires balance within it. This idea also applies to time. Time does not press forward, demanding resolution. It allows processes to unfold fully. Some changes happen quickly, others take ages. Both belong. There is no universal tempo that everything must follow. The universe accommodates many paces at once without conflict. Seen this way, motion is not something to be resisted or escaped. It is something to be allowed to settle. When movement is understood as persistent but gentle, it no longer feels intrusive. It becomes part of a steady background that supports continuity rather than interrupting it. The universe has maintained this balance for as long as it has existed. From its earliest moments of rapid change to its present state of vast, slow evolution, motion has never vanished. It has shifted, redistributed, and softened. Yet it remains fundamental. There is no indication that this will change. As conditions continue to evolve, motion will adapt rather than end. Activity may become quieter, interactions may become rarer, structures may thin and disperse. Still, movement will persist in forms appropriate to those conditions. This persistence does not imply endless intensity. It implies endurance. The universe does not need to be busy to remain alive with change. It can be calm and active at the same time. Motion does not contradict rest. It supports it when allowed to flow naturally. Understanding this can bring a sense of ease. The cosmos does not demand attention. It does not require intervention. It unfolds according to principles that are stable and consistent. Motion continues without needing to be managed or controlled. As this story comes to a close, it is enough to hold on to this simple idea. The universe stays in motion, not as a source of noise or disturbance, but as a quiet foundation. Change continues, gently and reliably, allowing structure, time, and balance to exist together. Motion does not need to stop for calm to exist. Calm emerges when motion becomes steady, predictable, and evenly distributed. The universe has mastered this balance on a scale beyond imagination. And within that vast, ongoing movement, there is room for rest. We, from Sleepy Stories, wish you a good night.